In order to replace the distributed loading by an equivalent resultant force and specify its location on the member AB, we can start by converting the distributed loading into a point load. It can be done by figuring out the area these distributed loadings are making. So to start, I have a rectangular loading having a height of 3 kilonewton per meter and a width of 3 meters. That is the span at which this distributive loading is being applied. Multiplying the two give us a point load of 9 kilonewton. Similarly, on the member CB, I have the loading of 2 kilonewtons per meter and it's applied at the span of 4 meters. If we multiply the two, it gives us a point load of 8 kilonewtons. Now these point loads basically act at the centroid of the area. So for the rectangular loading, it acts at the middle point of member AB and BC respectively. Now let's go ahead and figure out the resultant force component along the x and y direction. Since in this case I have just one force acting along the x, that is of 8 kilonewton going towards the left, that's why it is given as negative 8 kilonewton. Whereas for the y or the vertical axis, we have just one point load of 9 kilonewton that is acting downward. That's why we have our value of negative 9 kilonewtons. Now, once we have the individual components, let's go ahead and figure out the magnitude of the resultant force by combining these individual components utilizing our magnitude formula. That is taking the square root of x component square term plus y component square term. If we plug in the numbers in the formula and simplify, we are getting our final value of 12.04 kilonewton. That is the magnitude of the resultant force. Now, once we have the magnitude, let's go ahead and figure out the angle this resultant force is making with respect to our xy axis. So to do that, we can utilize our tangent inverse function. That is taking a tangent inverse of the magnitude of y component of the resultant force and dividing it with the magnitude of the x component of resultant force. In this case, we have the value of 9 and 8. Simplifying and plugging in the formula, we get our angle of 48.37 degrees. Now, one thing to keep in mind, we have just utilized the values and not consider the sign yet. The sign is basically telling us in which specific quadrant this force will be directed. Since I have both x and y component as negative, our force is in the third quadrant, so our angle is measured from the negative x-axis. Next, let's go ahead and draw the resultant force on the member AB because we are looking for the line of action at which the force is going to intersect the member AB. So we can go ahead and place the force at some arbitrary point x, and then let's solve for that particular value of x utilizing our moment equation. So here I have just drawn our location of the force from point A at a distance x. Next, to figure out this distance x, we can utilize our moment equation. That is, the resultant force moment at point A will be equals to the sum of moment of all the forces with respect to point A. Now, to start, let's figure out the resultant force moment at point A. Now, since our resultant force is acting at an angle of 48.37 degrees, it can be further converted into the two components or the two components that we started with. I have a vertical component of 9 kilonewton acting downward and the horizontal component of 8 kilonewton along the line of the member AB. Now, since to calculate the moment, the horizontal component in this case won't create any moment since it is passing through point A, and it will just have a pushing effect and no turning effect in this case, whereas the 9 kilonewton has a moment arm of x, and this is going to create our clockwise moment, so we represent it as negative 9x. Next, let's figure out the individual two forces moment. In this case, I have a 9 kilonewton that is acting vertically downward, and we have already discussed that it will act at the centroid of the rectangular area, so in the middle of it, so our moment arm is 1.5. So in this case, it is also creating our clockwise movement. Similarly, I have that 8 kilonewton force that is having a moment arm of 2 meters. Multiplying the two, it is going to create our clockwise movement as well. Now, once we have place everything in the equation, let's go ahead and simplify this. We are getting our value of 9x equals to 13.5 plus 16. Simplifying, we get our value of x as 3.28 meters.